Hello everyone, welcome to lecture 17 on Mechanics and Materials 1. This is our second lecture on the topic bending. We will have 4 lectures on this topic, and in this one we want to talk about section 6.2 on chapter 6 of the Hibbeler book. So the first thing we want to talk about today is the so-called jump condition. So basically what we want to see is that if we have a concentrated force or a concentrated moment, what sort of jump we get in our shear and moment diagram. You can imagine that due to a concentrated force, we should see a jump in the shear force diagram, and due to a concentrated moment, we should see a jump in the moment diagram. So we want to analyze that a little more carefully, and understanding that will help us to formulate the problems such that we can have a graphical representation for shear and moment diagram. This is what we want to do in this lecture. Before I proceed, I want to remind you of our plus convention. So this is the picture of our plus convention. Again, you remember, if you have a cutout of your beam, the plus convention for the shear force is such that it would cause, let's say, a clockwise moment. So on the left hand side, V should be upwards. On the right hand side, it would be downwards, in accordance with our plus convention. And then for the moments, they should deform the member such that it holds water, basically. So this would be also our plus convention. Obviously, for everything that follows from now on, we will also be using this convention. So let's look at the shear force first. So if you have a piece of a beam, it could be a much longer beam, and we are looking only at a little piece inside it. And then somewhere on that piece, you apply a concentrated force F, and let's say you have an upward force F. We want to know what happens to the shear force if you have this kind of loading. In order to see a better picture of this, we are going to enlarge this little piece, this incremental piece. We will enlarge it. Now on that piece, you can draw the force. It's an upward force, and it's a concentrated force. On the left hand side, you have a shear force VL. On the right hand side, you have the shear force VR. And then again, if you look at their directions, they correspond to our plus direction for the shear force. Okay, once you have this picture, you can write equilibrium for that. So you can sort of look at it as if it's a free body diagram of a system, and then you write the equilibrium of forces in the y direction. Assuming that upward is plus, then you would have plus VL plus F minus VR equals 0, which in turn tells you that VR equals VL plus VF. In other words, the shear force on the right hand side is equal to shear force on the left hand side plus the force F. If you want to draw it and look at it from the perspective of a shear force diagram, so this is your internal shear force and this is your coordinate x. If you come from left to right, the shear force would be VL until you reach the point that you apply the force F. Then you get an upward jump, and then you would have VR. So this is your shear force diagram if you have a concentrated force. So basically what we learned here is that an upward force or an upward concentrated force will result in upward jump in your shear diagram. So this was the case for the shear force. Now what we want to do is to do exactly the same thing for the moment diagram and see how you would accommodate for a concentrated moment, for an external moment, or how an external moment would influence the distribution in the internal moment in the beam. So now we look at this picture. Let's say again you have a cutout of a beam, and somewhere there you apply a moment MO. So this is an external moment, and also it's counterclockwise. So if you assume that counterclockwise is plus direction, this would be a plus or a positive moment. We do exactly the same thing. We enlarge that piece, but now we write equilibrium equations for the moment. In this case, the equilibrium equation would be the balance of moments, basically. And if you do that, you can say the sum of moments is 0. In this case, you have the moment on the right-hand side, mr, and assuming that counterclockwise is plus. So look at this. This is our assumption. So you get mr with a plus sign. You get mo also with a plus sign. And then you get ml with a minus sign. So this would be your equilibrium equation, mr plus mo minus ml equals 0. In other words, mr equals ml minus mo. More specifically, the moment on the right-hand side is the moment on the left-hand side minus the external moment. This minus must be compared with the plus that you have here. So basically that means if you draw the shear, if you draw the moment diagram for this case, you can see that if you come from left to right, and if at some point you apply an external moment MO that is positive, that is in the counterclockwise direction, the counterclockwise moment would result in a jump of moment, but now the jump is downwards. Okay? So basically, if you want to compare these two cases, again, you can look into this. In the previous case, for an upward force, you would have an upward jump in the shear diagram. For a counterclockwise moment, you would have a downward jump in the moment from left to right. So again, basically summarizing this, you can see that you get a jump of shear force due to concentrated force, and you see a jump of bending moment due to concentrated moment. All right, so this is our first message here. This is understanding the jump conditions. What we want to do next is to study the same thing, or basically to approach the same problem, but now dealing with distributed loads. Now imagine you have this beam with a distributed load on top of it. It could also include a concentrated force somewhere, or it could also include a moment somewhere. But now we want to talk about the part that deals with the distributed load. So we already know what happens due to the external moment and external force. What we want to learn is what happens due to distributed load. And what we do is exactly what we did previously. We take a little incremental piece of the beam and enlarge that. Or you write the reactions on that and also enlarge that. In this case, if you write the reactions, you would have the force V upwards on the left, downwards on the right. Remember previously we called this VL and VR Now we treat that a little more maturely, and we call that V plus delta V. So the shear force on the right hand side is the shear force on the left hand side plus a change in shear force. And the moment on the right hand side is the moment on the left hand side plus the change in the moment. And also again, remember that for this picture, we are following our plus convention for shear and moment. Okay, so this would be the shear force and moment on the left and right hand side. The length of that is delta x of that piece. Now for the external forces, if you think of a very little piece, you can assume that the distributed force is almost uniform. So basically it creates a rectangle here. Now the equivalent force of that rectangle would be the area of the rectangle, which is W delta x applied exactly at the center of that piece. So basically the distance would be 1/2 of delta x. All right, so this is basically the picture. Now what you want to do is to do exactly what we did before. We treat this picture as a free body diagram and we write equilibrium equations on that. So equilibrium of forces first. That would be the balance of forces in the y direction in this case, assuming that upward is positive. So V is upward, V plus delta V is downwards. So you get V with a plus sign, V plus delta V with a minus sign, and omega delta X is also upwards. This equation results in delta V equals omega delta X or W delta X, depends if you, so this is W basically, W delta X. One thing that I need to mention is that we assumed here that the distributed force is uniform. As you can see in the picture, it's not uniform. But this is not a problem because if this delta x is small enough, you can imagine that in that little piece, the assumption of having a uniform load is not wrong. It's a sensible assumption. It's feasible. So this is the balance of forces. So delta V equals W delta X. Then we write balance of moments, for instance, with respect to point O here, assuming that counterclockwise is positive, then you get minus M because it's clockwise. M plus delta M is counterclockwise, so that comes with a plus. So this is minus M plus M plus delta M. So this is the one on the right hand side. Then you have the moment due to the force V, and you have the distance delta x, and that would cause a, let's say, a clockwise rotation. So you get minus V delta x. From the concentrated force, the distance is 1/2 of delta x. It's upwards, the distance is delta. So the distance is 1/2 of delta x. The value is a W delta x. And then you get a minus because it will cause a clockwise moment. So you get W delta x divided by 2. And if you reorder the terms, you can see that delta m equals V delta x plus 1/2 of W delta x squared. So now that we have these incremental equations, what we want to do is to ask ourselves, what happens if delta x goes to 0? So if the incremental piece is very small, what happens then? Well, what happens then is that the first equation, delta v equals W delta x, it becomes dv equals W dx. Or otherwise, you can basically say dv over dx is w as a function of x, or in short, you can say v prime equals w. For the blue equation, if delta x is very small, delta x squared is negligible, so we ignore this term, and then you see the relation here holds dm equals v dx, or otherwise you can say dm over dx is v, or m prime equals v. So these are the relations. So m prime equals v and v prime equals w. These are the equations that we actually saw in the previous lecture. So we saw that these equations hold, but we didn't know why. You can see that actually you can prove them. So what we learned from this picture is that W, the distributed load, is the slope of the shear diagram, and V is the slope of the moment diagram. Alternatively, you can write this and you can think about them in terms of integrals. If you do that, delta V would be the integral of W delta x, or W dx. Delta M is integral of V dx. And basically, you would say that delta V is the area under distributed load, and delta M is the area under shear diagram. So basically, if you have a distributed load, you can draw its diagram, you can calculate the area under that, you calculate V, then you integrate it again, so you calculate the area of that again, and you calculate M. Putting these all together basically tells you that you can have a graphical method for constructing shear and moment diagrams. And that is exactly what we want to do in the rest of this lecture. Everything you need to know is already in this slide and in that previous slide where we talked about concentrated forces. So this slide and this slide basically. Knowing this, having these in mind, it's enough for you to establish a graphical method for constructing shear and moment diagram, and we are going to learn that through a set of numerical examples or exercises together. Exercise 1 of this lecture is similar to problem 6.5 on page 270 of the book. Draw shear and moment diagram for the beam shown in the figure. So as you can see, similar to the previous exercises that we had in the previous lecture, and also similar to the exercises that we have in the current lecture, so the remaining exercises, the question is always the same. Draw shear and moment diagram. Now, when you are asked to draw the shear and moment diagram, you have two options. Either you can do it like we did in the previous lecture, so you can actually calculate those, so v as a function of x, m as a function of x, you can calculate them as functions and then draw them. This is what we did in the previous lecture, and it's perfectly fine if you want to do that, but you can also do it using a, let's say, a graphical approach that we want to do now, and based on what we have learned in this lecture. So this is more like a shortcut towards drawing the shear and moment diagrams without calculating them actually. So this is the beam. You draw the free body diagram. So this step is always the same. You need to draw the free body diagram for the entire system, and you need to calculate the reactions at the support or multiple supports if you have more than one. In this case, you have only one support. So at the support A, or at the point A, you have two reactions. You have AY and you have MA. you can clearly see that AY must be 2 times P upwards to cancel the forces that are downwards, the external forces. And then the moment at point A, it must be minus 3PL, assuming that you draw it like that. So basically, this would be the opposite. This would be 3PL counterclockwise. Now again, the reason we draw it like that is because of our plus convention. So remember, the plus directions were like this. All right, so basically having said that, now you know the force and the moment at point A. And what you want to do is to calculate the shear diagram and moment diagram. Again, without actually calculating the functions. What you can see first is that the loads, the external loads that we have, these are just concentrated loads. So we do not have a distributed load. Now, if you remember, we said that V prime is W, or otherwise we said delta V is the integral of W dx from, let's say, point A to B. Now, considering that W is 0, you know that V prime is 0, or otherwise you know that V is constant. So the slope of V would be 0. That means if the V is 2P, which is the reaction at A, it has to remain constant with the slope 0 until you reach the point where you apply a force P. And now the force is downwards, so you get a downward jump because you have a downward force. And then you have, again, a constant V until the end. So that's it. That's basically your shear diagram. Now, the moment diagram, we can also draw it similarly, but remember again that the derivative of the moment diagram now is V. Or otherwise, you can say delta M equals integral of V dx. So basically, you know that the moment starts from minus 3PL. Again, minus is because of the sign. So this is the opposite of the sign that we had assumed as the plus sign. So it's minus 3PL. Then it has a slope 2p because m prime again equals v, and v is 2p from point A until the center. So you would have a line with the slope 2p until you reach the center. And after that, you would have a line with the slope p until you reach 0. And then again, at the end, the moment is 0 because it's free. So there is no moment applied here. So the moment must be 0. So basically, if you want to think of the equation of this line, usually if you think of just in a usual sense of a function, y equals mx plus b, slope m would be 2p and b would be minus 3pl. All right, so this is the answer to this question. As you can see, you can draw the shear diagram and the moment diagram without calculating them. Again, similar to the previous lecture, you could have calculated them. You could have just calculated these functions and then draw them afterwards. Either way, it's correct, But what we did here is the graphical approach towards drawing shear and moment diagrams. So it's like a shortcut. We will have more exercises on this and we will learn this better together. Exercise 2 in this lecture is similar to problem 6.6 on page 271 of the book. Again, the question is exactly the same question. You are asked to draw shear and moment diagram for the beam. Now the beam is simply supported and you apply a moment MO clockwise at the center of the beam. Similar to before, you start with the free body diagram. So you apply an external moment MO at the center and you want to calculate the reactions at the supports. In this case, if they are points A and B, the reactions would be AY and BY. So these are forces only in the vertical direction. Because the left support is essentially a pin, the right support is a roller, you do not have a moment at the support. So the supports do not apply any moment. Now, in order to calculate the reactions, you have again two unknowns. You can write your equilibrium equation. So you would have two unknowns, two equations. You can calculate the reactions. The first equilibrium equation is balance of forces in the y direction that gives you AY plus BY equals 0. The second equation would be balance of moments, for instance, with respect to A equals 0, assuming that counterclockwise is positive. Then you get minus MO because it's clockwise, and from BY you would get a moment By times 2L, which is the distance in the counterclockwise direction, so with a plus. And from two equations, you can calculate AY and BY. So BY would be M0 divided by 2L upwards, and AY would be M0 divided by 2L downwards. Okay, so this would be our point of departure now. We know the reactions at the supports, and what we want to do now is to draw the shear diagram. And then once we have the shear diagram, we can draw the moment diagram from that. Remember again, to draw the shear diagram, the key relation here is V prime equals W. And because there is no external force, W is 0. So there is no distributed external force. W is 0. And therefore V prime is 0, telling you that V must be constant. So V is minus M0 divided by 2L. Again, the minus comes from the fact that we had this convention for the plus direction of shear forces, and you can see that the shear force on the left cut, basically, or on the left end, must be upward to be positive. This one is downwards. So you would have minus M0 divided by 2L, and that would remain constant all over the beam until you reach the end, and then it comes to 0. Now that you have the shear diagram, you should remember that M prime equals V. You know V is constant now. So because V is constant, M would be linear. And you know M at the end, at the support here, because it's a pin, is 0. So it would be linear. The slope would be minus M0 divided by 2L. So basically you would have a line which looks like this. The equation of the line is minus M0 over 2L times X. So this is your moment. And then again, you should compare this with your generic equation y equals mx plus b. B is 0 because moment at 0 is 0. And m is the slope of the line, which is in this case the shear force, and that is constant, so minus m0 divided by 2L. So this would be the line until you reach the center of the beam. Then at that point, you have an external moment m0. So if you remember, if the external moment m0 is clockwise, you get an upward jump in the moment diagram. So you get this concentrated moment jump, or you get a jump in the moment due to concentrated moment. So basically, right next to the point at minus m0 over 2 from the left hand side, you would have m0 over 2 from the right hand side. But then again, you start from that point and the slope of the line is minus m0 divided by 2L, similar to the slope of the line here. So these two lines are parallel because they have the same v, they have the same slope. And then at the end, again, the moment would be 0, which is no surprise because at the end, you know, you have a roller and it also cannot support any moment. So basically, if you wanted to write the equilibrium, if you wanted to write the equation for the moment, similar to what we had done before, you could just think of it as mx plus b. And then here, the slope, the m slope would be minus m0 over 2L times x. And b would be your basically what you would have here. Okay, or otherwise you could basically write it in terms of x minus L and just add the moment that you have in the center. All right, so this is our second example, and as you can see, again, just starting from this picture without actually calculating the functions vx and mx, we managed to draw their diagrams, the shear and moment diagram. Exercise 3 in this lecture is similar to problem 6.7 on page 272 of the book. Again, the question is the same question. Draw shear and moment diagram for the beams shown in the figure. So you have two beams here, both under distributed load. One is a uniformly distributed load and one is a linearly decreasing distributed load. And what we want to do here is to draw shear diagram and moment diagram using the graphical approach that we just learned in this lecture. Pay attention that we are not interested to calculate Vx and Mx separately and then draw the diagrams. You can obviously do that, and sometimes you may be asked to do that, but right now that's not the question. You are asked to just draw them using the graphical method. So we do that here together in the same slide. On the left hand side, this would be the one with a uniform load or with a uniformly distributed load. That's 3 kilonewton per meter. The length is 4 meters. So the equivalent force of that would be 12 kilonewton in the center. And that tells you basically that at the support, you would need a force of 12 kilonewton upwards for the balance. And you would also need a moment of 24 kilonewton meter counterclockwise, because the distance here is 2 meters, and if you multiply 12 by 2, you get 24 in the, let's say, clockwise direction. So the reaction at the support would be 24 kilonewton meter counterclockwise. Now remember, again, our plus convention is this. So basically, on the left hand side, having a moment 24 kilonewton meter counterclockwise, it eventually means minus 24 when you want to draw the moment diagram. All right, so we start with the shear diagram. Again, remember that V prime is W. Now, W is constant. That tells you that V prime is linear. But also W is not only constant, the constant is minus 3. So it's 3 downwards, which tells it's minus 3. And essentially that means that you have a line for shear force that is having a slope of minus 3. So it starts at 12 kilonewton, and then again 12 kilonewton is upwards here, so that's plus according to our convention. It starts at 12, it has a slope of minus 3, it has the length 4, and at the end it comes to 0. So this is your shear diagram. And then again, the fact that it comes to 0 at the end is no surprise, because at the end it's free, so there is no single force applied there, and basically you would have a 0 at the end. So the next thing we want to do is to draw the moment diagram from the shear diagram. For doing that, you can remember that m prime equals v, or otherwise you can imagine delta m equals integral of v dx, or the area under the shear force diagram would be m. So the moment at A is minus 24, and because v is a linear function, m must be a quadratic function. And it should also end at 0 at the end, because you have no concentrated moment applied at the end of the beam. So basically you start from minus 24, you draw a quadratic function which ends at 0 at the length 4 meter, and that would be your moment diagram. Okay, now that you have this, we come to the second case where you have a linearly decreasing distributed load. It starts at 2 kilonewton per meter at 2 kilonewton per meter on the left hand side all the way to 0 on the right hand side. So again, we start with the free body diagram, and we need to calculate the reactions at the support A. You draw them according to our convention. So the area of the triangle is 1/2 of 2 times 3. So it's 3 basically, 3 kilonewton. That's the area of the triangle, telling you that you would need a force of 3 kilonewton upwards to have equilibrium. And that force, that equivalent force, would be applied at the distance 1 meter, telling you that the moment must be also 3 kilonewton meter and counterclockwise, which is the opposite of the direction that we assumed to keep equilibrium. Now again, remembering that V prime is W, but in this case W is linear, you know that V must be quadratic. So it's a quadratic function. It's a quadratic function starting at 3 and decreasing all the way to 0, and we know that the slope is always negative. So at any point V prime is W, so we know the slope at any point is negative, so it should always be, let's say, decreasing. Now, once you have the shear diagram, you can also draw the moment diagram using a similar approach. M prime equals V now, and then because V is quadratic, M must be a cubic function. So M is a cubic function, but you can see that the slope of M is V. So M prime equals V. So that means the slope of M is V, but V is always positive. So it basically tells you that if you start here, you always go with a positive slope until you reach 0. And the slope is decreasing the further you go. Basically, at the beginning, you have a higher slope because V is larger. And the further you go, the slope gets smaller and smaller. But it's always positive because V is always positive. All right, so basically using our graphical approach, we can also draw the moment diagram. Exercise 4 is similar to problem 6.8 on page 273 of the book. Again, you are asked to draw the shear and moment diagram for the beam shown in the figure. Now you have a cantilevered beam on which you have a concentrated force 2 kN downwards at point A and a uniformly distributed load 1.5 kN per meter from center to point B at the right end. To begin, we start again with the free body diagram, assuming that the coordinate x starts from point A. So the left hand side would be corresponding to x equals 0 and the right hand side would be later corresponding to x equals 4 meters. We proceed. Now on point B, you draw the reactions at the support, assuming that this is MB, and we draw it counterclockwise, and this is BY. We draw it upwards. For the distributed load, 1.5 kN per meter, you can imagine that the effective load would be 1.5 times 2, that is 3 kN downwards. So you would have 3 kN downwards with the distance 1 from each side. So it's at the center of the distributed load. Now for this picture, you can write the equilibrium of forces and moments. The equilibrium of forces would be the equilibrium of forces in the y direction. You have By upwards, then you have 3 downwards here, 3 kN, and 2 kN downwards here. So that tells you By must be 5 kN upwards. So this is the reaction at the support. Then you can write the equilibrium of moments with respect to point A, for instance. If you do that, then you would have MB with a plus, assuming that counterclockwise is a plus direction. So you would have plus MB minus 3 times 3. Now, 3 is the distance here, but also the force is 3. And then it will cause a clockwise moment. So it comes with a minus. So minus 3 times 3 plus 4 times B. So By is upwards, 4 is the distance, and it will cause a counterclockwise moment. So it comes with a plus. So minus here is clockwise, basically, plus is counterclockwise because we assume that counterclockwise is plus. So if you do that, you calculate MB, and that would read minus 11 kilonewton meter. Now, using this information, you want to draw the shear force diagram and the moment diagram using what we just learned. So again, if you remember, V prime equals V prime equals W, and M prime equals V. So from point A to the center, there is no external force, there is no distributed force, so W is 0 here. W0 tells you that in this portion, V would be constant, and V constant means M linear. So this is for the first portion. Then for the second portion, W is constant, therefore V is linear, and M is quadratic. So basically, from A to the center, so for the first portion, it's very easy to draw the diagrams. You can calculate the shear force at any point between A to the center, and that would be -2, and it's always constant, -2. The reason, again, is that you have just 2 kilonewton downwards. Or if you remember at the beginning of the lecture, we talked about jump condition. So you can imagine that the shear force here is 0. And then if you come from left to right, you have a concentrated force downwards. So you would have a downward shift of the shear force. So shear force would be -2 at point A, and it's constant -2 because there is no distributed load. Therefore, the slope of V is 0 until you reach the center. Now, from the center, you would have a linear function. Now, it's linear because W is constant. It's a linear function that goes from -2 to -5. Now pay attention that here we calculated By to be 5 kilonewton. Why is it -5? It's -5 because if you remember the plus convention that we had, this would require V to be downwards on the right hand side to follow our plus convention. So here By, the way we draw it, it's 5 kilonewton upwards, which means according to this convention, according to our plus convention, this is -5. Okay, so this is your shear diagram. Now having the shear diagram, we can draw the moment diagram. For the moment diagram, you know the moment here is 0. You also know the moment at the end is -11. You have already calculated it. So you start with 0. With the slope of -2, you draw the moment diagram until the length 2. So you would reach -4. This is a line with the slope 2, or with the slope -2 basically. Then from -4 to -11, you would have a quadratic function, but at any point of that, because m prime equals v and v is negative, at any point it would be decreasing. Okay, so the slope of that should always be negative. And it would be increasing. So we know it's going to be a quadratic function like this, and we know at the beginning it's not 0, at the end is not 0 or infinity or anything, because we have this slope. The slope at the beginning is -2, at the end is -5. Okay, so basically now using our graphical approach, we have the shear diagram and we have the moment diagram, also for this fairly complex example. Exercise 5 is similar to problem 6.10 on page 275 of the book. And then again, you are asked to draw the shear and moment diagram for the beam shown in the figure. Here, the beam is supported by two bearings. Pay attention that at A, the bearing is a thrust bearing, and at B is a journal bearing, meaning that at A, it's fixing it in the axial direction, so it doesn't allow for the horizontal motion. But at B, it doesn't add that additional support, but also you know that they do not apply any moment. Okay, so this is the beam under a linearly increasing distributed load. And in order to analyze that, again, we start with the free body diagram. So from A and B, we draw the reactions AY and BY as upward forces to begin with. The effective force here would be the area of the triangle. So that would be 2. That's the height here is 2 times 4.5 length times 1/2. So that's the area of the triangle, which would be 4.5 kilonewton. And the distance would be 1/3 of the length, which is 1.5 meter. So you have the equivalent force, 4.5 kilonewton at a distance 1.5 meter. And then for that, or from that, basically using the equilibrium equations, some of the forces in the y direction is 0, some of the moments with respect to, let's say, A is 0, you can now calculate the reactions at the supports. And if you do that, you get 3 kilonewton at B and 1.5 kilonewton at A, which makes sense. Again, if you look at the force here, the distance is 1.5. The distance here is 3. So 3 is 2 times 1.5, and basically that tells you that BY must be 2 times AY. And that's what you see here. All right, so once you have the reaction at A, so you have AY equals 1.5 kilonewton, all you need to do is to basically proceed and draw shear and moment diagram. Now, what we have done before was more similar to this. We start at the distance x. You can calculate v and m as a function of x by integrating the area of the triangle and proceed with that. But what we want to do now is to, again, use our graphical approach instead of exactly calculating the formula and drawing the diagram. For doing that, again, you remember that v prime equals w and m prime equals v. So at A, the internal force, the internal shear force starts at 1.5. Then because V prime is W and W is linear, so it's linearly increasing, but it is downward. So it's with a negative sign actually. So you should remember that 2 kilonewton per meter, it reads -2 because it's downwards. So because W is linear, you know that V is going to be quadratic. So basically you start at 1.5 with a negative slope and with an increasing slope. You draw your quadratic function. And you know at the end it's going to be -3. So basically you want a quadratic function that starts at 1.5. The slope at the beginning would be 0. At the end, the slope is -2. And we know at the end it's going to end at -3 because that's the reaction at B. So you draw that quadratic function and you get V. Also, you can see that at the distance 2.6, your V would be 0. Now from V, you can also calculate M using M prime equals V. But now because V is quadratic, M would be a cubic function. What we do know though is that M would be 0 at both ends. You know the slope of M would be V. So it's at the beginning the slope is 1.5. At the end the slope is -3. And at 2.6 the slope is 0. And there is only one point where the slope becomes 0. So there is only one maximum. And using this information, you can draw the cubic function for M as shown in the figure. Again, this is now your shear diagram, and this is your moment diagram using our graphical approach, but you could have just alternatively used what we had done before. You could have calculated exactly V as a function of X, M as a function of X, and then draw them. And you would end up with the same graphs. All right, so this was our lecture 2 on the topic bending, the second part of the 4-part series on bending. And today we covered section 6.2, which was essentially about graphical representation of shear and moment diagram. We will have 2 more lectures on the topic bending in the following weeks.